Welcome to the Probability and Statistics course. Today's lesson is on linear regression. What linear regression is about relationships between variables. So we have talked about the importance of having samples and studying what's happening in these samples in order to draw conclusions about populations. In this case, we are going to have, let's say, two samples. We could have more, but in this lesson we are going to talk only about two samples. And we are going to study to see if there are any relationships between the two samples in order to draw conclusions about the populations, if there are any relationships about the characteristics of two populations. Now, we are going to talk about linear regression. We are going to see what scatter plot is. We are going to talk about the correlation coefficient. And finally about the regression line. Now, as we said, we are going to talk about if there is any relationship between two or more variables. For this lesson, we are only going to see two variables. First of all, we have variable y, we are going to call it y, and it's going to be our response variable. The other variable, x, will be called the predictor variable. Now, y is usually the one that is dependent on the other, and the other is the independent one. Of course, the distinction between dependent and independent variables is not so clear many times. So, most of the times we have to decide which one will be y and which one will be x, depending on which one we would in the future like to predict, giving a value for the other one. We are going to see this in more detail later on. Now, let's have a look at some scatter plots. We see here 4 different examples. Now, scatter plots are other kinds of plots. We have seen that when we have some samples, we should usually make a picture so that we have a first idea about what's happening. In this case, when we do regression, when we are searching about relationships between two variables, we need to construct a scatter plot. A scatter plot is a plot which consists of variable y and x. We have here variable x, variable y, and we see different pictures. Now we can see that we are looking at the overall pattern of these pictures, and we see that there are different forms, of course, different directions in the patterns, and later on we are going to see that there is different strength, as we say, in the pictures. So let's take one by one and see it closely. First of all, this first picture, we see that we cannot find a certain pattern. We can see data actually like they are all over the place with not a particular picture to see. So in this case, in cases like that, we would say that we cannot find any relationship between two variables. We cannot say that one variable depends on the other one. Now, our second plot, our second scatter plot, we see here that we can see something that data, we can distinguish data in orange here, which look like they form a straight line. We can see the blue line on top of this data. So we can understand that for this kind of data, we feel that there is some relationship between the two variables, that x and y, y may depend on x. Now, when there is a relationship, we want to see what kind of relationship these data they have. Because we can assume that there is some straight line that could describe this kind of relationship, we are talking about linear relationship. Later on, we are going to see non-linear relationships, just have a picture of non-linear relationships, although in this lesson we are only going to discuss about linear relationships. Now, also, in this picture, we can see that there is a direction, there is an upward direction of our line. So, we are talking about a strong, positive, linear relationship. Now, the strong is the strength, as we said, because in this picture here, actually the data, they are very close to the line. They could, in other cases, we could have a picture like, let's draw here, we could have again data that they show a relationship. They show some kind of linear relationship, but they could be not so strong. So we see that here again we could say that we observe a pattern, a line, but not so strong as the picture we've seen in our example. So also a characteristic of the relationship should be to measure the strength of the relationship each time, for our case of the linear relationship. So every time we describe some sort of relationship, we have to say what kind of relationship it is, here a linear. If it is for the linear case to distinguish between positive or negative, if there is an upward or the other way around direction, and talk about the strength of the relationship. Our third plot we see here, again, we are talking about linear relationship. Again, our data look like they form a straight line. Now, it is a negative one because we see that we have a direction, an opposite direction than the positive one. And again, we are talking about a strong relationship, as we see that our data look very close to our line. Our fourth plot here, we see that some data here underneath this line, they form some kind of pattern. We see that we can see a pattern is they are not all over the place as we've seen in our first picture. So there is some relationship, but this relationship is not linear. So in this case, we are talking about non-linear relationship. Depending on the picture we see, we have different forms of non-linear relationships. But we are not going to see any in this lesson, so we are not going to talk about the different cases. We also distinguish between different strengths of nonlinear relationship. We actually see here that our data, they form exactly the picture we see here, the line we see here. So it's a very strong relationship, but for nonlinear relationships, we cannot talk about direction. We don't have a positive or a negative. It is important that we distinguish between nonlinear relationships and no relationships at all. Not having a linear relationship, it doesn't mean that there is no relationship. We could have a nonlinear one. So if we conclude that there is not a linear relationship between two variables, we cannot say that they do not have a relationship. Now, the strength of the relationship can be measured if we calculate the correlation coefficient. The correlation coefficient is denoted by the small letter r and measures only the strength and direction of linear relationship. This is very important, that correlation coefficient, as it's going, we'll see how we can calculate it, measures only for linear relationship, no other kinds of relationships. Now, the correlation coefficient is a number between -1 and 1. We're going to see what these numbers mean in each case. So R, the correlation coefficient, can be calculated using this formula here. Now, when we see different examples, we are not going to take data and calculate one by one this formula, as most packages, software packages, can automatically calculate this number. So, but if somebody wants to work by hand, he needs to substitute here, as we see, n, the number of data we have, the number, the sample x, the sample y. Now here only we are going to see what's the difference between this and this. So what we have is that if we have, say, a sample y and x for a variable y and x, let's say I just write down some numbers. We don't mean something, just to see what we mean. Is that when, in the first case, when we have a sum of xi, yi, we actually mean multiply one number with the other and add up, multiply the second with the other, and so on. So it's 1 times 0.5 plus 2 times 0.6 plus 3 times 0.7 plus 4 times 0.8. When we have sum of xi times sum of yi, we first sum up. So for xi is 0.5 plus 0.6 plus 0.7 plus 0.8, and then multiply with the sum of the other variable. So we understand that actually these two calculations are different. We have to be careful that this is different than this. Now, let's go back to our correlation coefficient. For this kind of data, we have that the correlation coefficient is close to 0 because there is no relationship. So what happens is that the correlation coefficient, depending on the number we are going to calculate, we can have an idea of what's going on. But always first have a picture because sometimes the correlation coefficient we are going to see in our next lesson could be misleading. But if the data, let's say, behave okay, they don't have some irregularities, we expect that the correlation coefficient will give us good information about the relationship. As we have seen in this picture, when there is no relationship, the correlation coefficient should be close to 0. So we write our different cases here. No linear, we said, the correlation coefficient measures linear relationship or not, no linear relationship. The correlation coefficient should be close to 0. Now, positive linear relationship, the correlation coefficient should be close to 1. And negative linear relationship, the correlation coefficient should be close to -1. So we see here that the sign of the correlation coefficient gives us the direction of the linear relationship. Positive, we have a positive sign. Negative, we have a negative sign. So let's have a look at our other pictures we've seen before and see what kind of, what number we should expect from our correlation coefficient. We have that. Here, for example, when we had the positive linear relationship, a strong linear relationship, we would expect our correlation coefficient, of course, to have a plus sign, as shown here, and be close to number 1. Of course, it's not exact 1, as they don't form exactly a line, but it is a number. 0.8 can be considered a number quite close to 1. For our other picture, we see that this is a more strong linear relationship. The data, they seem to be more close to our line. So our number, we see 0.9 is more close to 1, to -1. The minus is the direction that we have a negative relationship. So it goes, the numbers go, here the line goes down. Also, when we have a non-linear relationship, we have the correlation coefficient being 0. So we saw that in our first case, as in our last case here, our correlation coefficient should be 0. But there are two very different cases. One, we have no relationship. The other, we have a very strong relationship, but non-linear. So when we calculate a correlation coefficient to be 0, we should see which case of the two we are. Either we have a no relationship at all, or we may have some kind of relationship, but non-linear one. Now we are going to talk about the regression line. A regression line is called the line that we would expect that the data will follow. Now, this line we have drawn here, somebody could say, why this and not another one? Why not this one? We don't know which one would be better for our data. So we are going to see methods in order to calculate in some way the best line that passes from our data. We're going to describe later on in which sense we are talking about best line. This line, the best line which is going to pass from our data, is going to be called the regression line. And it's called regression line because of the method we are going to use in order to calculate it. We are going to use regression. Now for this line, we have, for every line, there are two characteristics, the slope and the intercept. We know that for a line from maths, we have that it's given by y equals a plus bx. And so we have A and B to distinguish between different lines. So B will be the slope, will be how much does y change when x increases by 1 unit, and A will be the intercept, the value of y when x equals 0. Will actually be, if we draw our line up to cut the y-axis, the value we observe here. So now let's see in which way we can calculate the best line for some data. We have that. Let's take only 3 points so we can understand exactly what's happening, and assume that a line passes from these 3 points. We still do not know which line is this. We just have drawn it in some way so we understand the method. But we would have to introduce a method in order to calculate A and B's in such a way so that our line would be the best. We still haven't said what we mean by best. Let's see then what we mean by best. So what we do is that we actually measure the distance between the points and the line. So you can see for these 3 points we have these 3 distances. What we do is that we measure this. We say that this distance is E1, this distance is E2, and this is E3. And then we would need to calculate the line, to calculate A and B in such a way so that these distances are the sum of these distances should be minimized. So we want that line that overall will give us not a lot distant from our points. Now, if we just add up the distances as they are, the problem is that we may have positive and negative signs because of the numbers here. We see that this will be greater than what would our line give, so this would be positive, but here we would have negative numbers, so we would have to be very careful of how we calculate the distances in order to have the positive numbers. In math, a usual way to not to have a problem like that is to actually square our numbers. So instead of working with the distances, we are working with the distances squared. So now the line, the best line that we would calculate using this method, every time we put a value x there, will give us an y, which will not be the y we know, will not be this point, but will be an estimate as it's called, and it's going to be the y hat. We denote it by y hat. So every time we give a number for x, we're going to take a y, not our original data, but a y on the line, the y hat. Let's go back to our method, see how we calculate the best line. We have that these distances are actually the difference between the value we have observed, our y, our data, and what would the line give us if we put the same x in our regression line. So this will be the distance, and by substituting y hat by a plus bx, we have that the distances are actually y minus a minus bx. Now, as we said before, instead of using this, as we don't know if it's going to be positive or negative, and there is no, it doesn't make sense to add up positive and negative numbers, then we won't have the measure we want. We square our differences and sum them up. We are going to look at overall the line to be the best in the sense we have described. And so we actually, by where EI putting y minus a minus b x, minus bx I should be here. We should have the indexes for each point. We have that. This will be equal to that. So, in order to calculate A and B's now, the only thing we would need to do is minimize this function. Now, we are not going to see how to minimize this function. Maybe by looking at the maths book, somebody can understand how to minimize functions. But the only thing we are going to see here is what is the result. So if we minimize this function, what we obtain is an estimate of our b, of the parameter b, which we write it by b hat, given by this formula here. And also an estimate for parameter a, which will be given by using the formula here. We have already estimated parameter b. Here, this is the sample mean of the variable y. This is the sample mean of the variable x. And so A can be calculated too. Now, as before, if we substitute where A and B, the estimates of them from our samples, we would have EI estimate, which are called the residuals. Now, when we calculated our regression line, we have actually made we have assumed a few things. We have made some assumptions. Although we haven't talked about these assumptions, this should be checked at some point. Usually they are checked after we find the regression line. We are going to talk about these assumptions in our next lesson. Now, for example, if we have some data, an example given here, if we calculate the regression line, we have that here y hat would be equal to this plus this number. This number, as we said before, should correspond, if we draw the line up here, should correspond to the number that the line intercepts with y-axis. Here we see that there is a minus sign. This minus sign, of course, is because we can see a negative relationship. Now, as we have observed using this method, the regression method, we see that our data are given, our samples are given in pairs. So when we plot the data, or when we do our regression, when we try to find our regression line, we consider our data in pairs. There is no problem if we change the order of the data they are given, as long as each point y corresponds to the original point x that we first had our data. We shouldn't just change the order of y and leave x as it is. They should be changed the same way, because each point y corresponds to one point x. Now, another measure is the coefficient of determination. The coefficient of determination can be calculated by taking the square root of the correlation, square of the correlation coefficient and multiply it by 100. What we are going to have in this case is the percentage of variation in y that can be explained by the least squares regression line of y on x. So, for example, if we had correlation coefficient b equal minus 0.9, then for this data, the coefficient of determination would be r squared 81. So we see that for the coefficient of determination, now we lose the information about the direction of the line, we lose the minus sign, and what it tells us, this 81, is that 81 of the variation in y can actually be explained by the regression line by the line we have calculated for our data. Now, both from the correlation coefficient, as we said, it's very easy to calculate the coefficient of determination. But from the coefficient of determination, in order to calculate the correlation coefficient, we may take the square root of it, but we should be careful if we should consider the negative root or the positive root, if we should include the negative or the positive sign. And this, of course, can be done by looking at the direction of the line. If we see an upwards direction, we use a plus sign. In the other way, we use a minus sign. So as we've said in this lesson, we've seen relationships. Actually, in particular, we've seen linear relationships between data sets. An example of linear relationship would be if we measure the weight and the height of a group of people. So what happens here is that, for example, we have one group of people. Now, for each one of this group, we measure the height and the weight. Now, we measure the height and the weight for the same person, because we are going to see if there are any relationship between variable height and variable weight. One of them would be our y, our response variable, and the other our x, our predictor variable. Which one is the response and the predictor? As we said before, it's not very clear. So in this case, if, for example, we would like to measure the weight and understand what's happening for the height, we should put y here and x as the weight. If we would like to measure height and see what's happening with weight, we should put the other way around. In any way, which way we put our variables, the same way we should consider our regression line. So y would correspond to height and x should correspond to weight. As we said before, when we calculate the regression line, we make assumptions. They are very important assumptions, although we haven't said that from the beginning. We have to check them in the end, and this is what we are going to see in our next lesson. So we've seen the linear regression here. We've seen the plot which we should do when we're talking about relationships, called scatter plot. We've seen the correlation coefficient, which measures the direction and the strength of linear relationships. And we've seen what the regression line is. For more information on this lesson, you should visit the webpage of Nettuno MedNetU project.